Welcome back. In section 3.1.5, we'll see Cayley-Hamilton theorem. So here's the theorem. Let A be an n by n matrix with, this is its characteristic polynomial, and it expands like this. Then if I plug in A into the polynomial, which really means that I'm taking a to the n, a1a, and then for A0, I need to turn it into a matrix, so I would multiply by the identity matrix of the correct size. Then this is going to be equal to the 0 matrix. So I'll have you prove it for certain types of matrices later this term once we have diagonalization done. But for now, let's just check it. All right, so let A be this matrix here. Verify that the Cayley-Hamilton theorem holds for X. All right, so I'm going to start by finding the characteristic polynomial of A, and then I'm going to plug in A and see what I get. All right, so characteristic polynomial, I'm going to take the determinant of 2 minus X, 1, 5, 3 minus X. So that's 2 minus X times 3 minus X minus 5. And so it's x squared minus 5x plus 6 minus 5. And so I get x squared minus 5x plus 1. All right, so now I need to plug in a into this polynomial. So I'm going to have to compute a squared minus 5a plus 1 times the identity matrix. That's the 2 by 2 because a is 2 by 2. Let me just compute a squared on the side. I get 4 plus 5, I get 9. I get 2 plus 3, I get 5. 10 plus 15, 25. And 5 plus 9, I get 14. All right, so that's 9, 5, 25, 14, minus 5 times 2, 1, 5, 3, plus 1, 1, 0, 0. So I get 9 minus 10 plus 1, that's 0. I get 5 minus 5, that's 0 as well. I get 25 minus 25, 0, and 14 minus 15 plus 1. And so that does give us 0, 0, 0, 0. All right, so we do get the 0 matrix. Let me say, this seems like a bit of a random theorem that is cute but doesn't have major consequences. It actually is very important in algebra. It actually leads to something called Galois theory, which is the way to prove that you wouldn't have a quadratic formula-like solution for polynomials of degree 5 or higher. All right, so it's super important. This idea actually led to so much more.